A short bio here. Guang Liu Ma is a professor of computer science and chair of the graduate group in computer science at University of California, Davis. He leads the VD research group and directs the DOE CEGRAPI Institute for Ultra-Scale Visualization. He received his PhD degree in computer science from University of Utah in 1993. Then he spent 6 years at the NASA Langley Research Center before joining UC Davis. His research interests include visualization, computer graphics, interface design, and high-performance computing. And please, Guang Liu Ma, just start your presentation. It's more than welcome. Thank you.
Yeah, thank you for the introduction, and thank you for inviting me to this conference. I really enjoying my stay, meeting new people, particularly the very rich cultural experience I can have here. So my research largely about dealing with big data. And big data is a popular topic these days. So I decided to talk about big data visualization, some of the works that we have done at UC Davis. So over the past 20 years, actually more than 20 years, I actually been working on both scientific data and social science data, information in general collected for a variety of purposes. So what I'm going to do today is just to present some of the projects we have in scientific visualization and information visualizations. I hope I can finish this in 40 minutes. Okay, do my best. And okay, let's just start by asking this question: how big? It's big. So I have been working closely with scientists in many different areas, and those scientists they run big simulation on supercomputer for their study. And here I have a few examples. In fusion plasma physics, nowadays each round of the simulation routinely dump around 5 terabytes to disk. And in a few years, they expect their simulation can output around 25 terabytes. But I want to point out, 5 terabytes doesn't sound a lot. But then, in fact, most of these simulations are already capable of generating petabytes of data. They just choose to output 5 terabytes subset because this cannot afford to store all the data they're capable of generating. And in astrophysics, this day they already can, they already store up to 100 terabytes per run. And certainly all these numbers are increasing. And in turbulent combustion simulation, I work particularly closely with scientists in this area. Their simulation routinely output over 300 terabytes per run. So that's a lot of data. Then I maybe, by the way, also mention non-simulation data. like what we expect to see the next generation telescope are capable of generating. So we're talking about 10 petabyte per year, right? 2015. And then this one in Australia, we're talking about 100 exabytes per year. Many years from now, but that's a lot. We're talking about 1 terabyte per second. So how you store all this data, how you make sense of data, how you utilize data for your scientific research, right? Discovery. So over the years, I've been helping my collaborator in various areas like supernova simulation people. I help them see their data in such a fashion, in this quality, this clarity, and this interactivity, and also allow them to see the complex interaction between different variables, different quantities. And here's another example in fusion. This one actually kind of straightforward, except the mesh structure is a little bit challenging to deal with. But then we directly render this potential field of this tokamak fusion device. But in fact, we also done a lot to help them visualize other aspects of data, which are actually much more challenging than just rendering the flow field. And the last example is turbulence combustion simulation. And combustion simulation generally output a very large number of variables and the chemical species. So we're talking about over 100 typically. And my collaborator, they often want to study the complex interaction between some of these chemical species and the variables. So we often need to help them visualize simultaneously, these 2 or more variables at the same time. So all these scientists we've been working with, they use supercomputer, and many of them actually been using the most powerful supercomputer in the world, operated at U.S. government national laboratories. And use this. So they run their simulation, as I mentioned earlier, right? Each run can generate petabyte of data, but then they only store a subset. But no matter what, they need to dump the data to some mass storage device. And then even today, most of them still rely on post-processing visualization and data analysis to study their data. That is, after the simulation is over, then they look at the data using a visualization cluster provided by the supercomputing center, or they move portion of the data back to their laboratory and look at it. So this data movement create a lot of problems. Just think about how long it would take you to move, say, let's just don't say 300 terabytes, right? Just 3 terabytes. How long would it take you to move, right, over a wide area network? So they really need help. And obviously, the best way is to further reduce the data that they have to move. Move and save and look at. So based on their domain knowledge, right, they already decide to store less data. For example, the turbulence combustion researcher we work with, they skip at least 200-300 time step. That is, they only store every 200-300 time step. So their simulation can run several days, and then outputting 100,000 of time step. But then they only store such a small subset. But still, that's still a lot, right? As I mentioned already. So the best strategy is to reduce the data right early, and that will really help all the following right steps. So today, I'm mainly just gonna focus on what we call in situ visualization methods. And the idea is very simple. Basically, we try to do something to the data, right? While the data are being generated, okay? Before writing the data to disk, we see what we can do, right? We either can visualize the data right there, right, during the simulation, or we reduce the data in an intelligent fashion, right? Or we can better prepare the data, right, for following post-processing visualization analysis. So there are different ways to do in situ visualization. So more than 10 years ago, I tried to promote in situ visualization, and I actually very pleased that everybody recognized this is the most feasible solution to this upcoming exascale computing challenge that we're gonna have. That is, there's no way as supercomputer become more and more powerful, and scientists, they want to solve more complex problem at higher resolution. The data only going to become bigger and bigger, and so we must come up with a feasible solution, and in situ visualization is such a solution. So what in situ visualization can enable? I already mentioned a few, but basically it can allow the scientists to use in situ visualization to monitor, right, their simulation, and they can reduce data while the data being generated, can prepare data for more efficient post-processing. And in fact, if done right, in situ visualization also can be used to drive the simulation, right? So that would be the optimal goal of the scientists. And certainly, in situ visualization can also help simulate the performance of the simulation, right? A lot of time, the scientists will want their simulation run more efficiently, so they could use in situ visualization to monitor the execution of the simulation code and see how the communication I/O perform efficiently or not. In situ visualization has not been widely adopted. Why? Because it requires great effort, not just from us, but also from scientists. We and the scientists must work very closely together, because we need to integrate for very efficient in situ viz. We need to integrate the simulation code and the visualization code. Right? Could be tightly coupled, could be loosely coupled, but then we need to work together. And the visualization solution must be low cost, because scientists, they want to use supercomputer to run their simulation. If your simulation solution would take 50% of the supercomputing time, then it's not acceptable. So we have to develop extremely efficient, particularly we're talking about supercomputer, massive parallel supercomputer. So all in situ viz solution must be parallelizable and must be highly scalable, such that it will become acceptable by the scientists. And there's many additional requirements, depends on the particular objective, but I'm not going to go over more here. So we have worked on in situ viz. Here I just use call in situ viz. It's like a more general term. We actually do more than just rendering. But here we have an example just to perform rendering of the data during the simulation. And so this is the turbulent combustion simulation code that we work with. And we actually look at both the volume data and the particle data together. And we previously developed a highly scalable parallel render. And we managed to only take a very small percentage of the overall supercomputing time. So we try to keep it actually under 5%, but then in most cases, it's only take like 1 or 2%. I'll tell you why. I mean, not only because our algorithm is highly scalable. And so we use this Cray XT5 computer, which has much larger number of cores, but then we only use up to near 16,000 cores. And with that, basically with this effort, we demonstrate that in situ viz is quite feasible. So here I have this test result, and all I want to show you is just pay attention to this small red block. This is the time for visualization. And the light blue block is the simulation, and the blue block is I/O. Okay. Remember, scientists, the I/O is not bad because scientists, they don't dump every time step, right? They skip. And then we don't render every time step. We maybe skip. Scientists, maybe they skip. They throw away every 200-300 time step. And we try to render every 10 time step. Okay. So as I mentioned, in situ visualization, a broader sense, it's not just about rendering, but also you might want to reduce the data when it's possible. And so there's a way that you can just apply conventional compression method, but then the compression solution must be parallelizable, and it must efficient, right? And particularly, we cannot just use lossy compression, right? The scientists, they spend all this effort, right? They run such high resolution, high precision simulation, and then you just compress the data and then throw away all this precision. That would be bad. So we have developed a lossy compression solution, and then actually we have a paper this year, and we achieve between 30% to 50% saving for lossy compression. So that's really good. And we also work on direct feature extraction and tracking as a way to reduce data based on the scientist's knowledge. So compression, this lossless compression method we have here, it's just we can apply to any floating point data. But then this feature extraction method is really based on scientists' domain knowledge. Like they already know they're looking for a particular type of feature, and they can somewhat define that feature. So we maybe can do in situ feature extraction, right? And then we only store the feature rather than the raw data. But what I want to go over a little bit more detail is this important-based visualization data reduction method that we have been working on. So, so this again is from this turbulent combustion simulation. This is a flame. So we know that scientists are very interested in studying the small turbulent eddies near certain feature surface. So they can well define the feature surface. And they would like to study those small eddies near the feature surface. But then if we just render the data directly, this clutter, right? It's the very complex turbulent flow. They cannot just based on simple transfer function and then remove this other part, right? This is just like this picture. So what we did is to develop an important space solution. In this case, we compute distant field, right, during the simulation. And basically, it's distant from feature surface. And we have developed a highly efficient parallel distant field calculation. And so that during the simulation, we can compute this distant field. And then, after the simulation, scientists, they can, right? They can, based on the distant field, okay, I don't have this, doesn't work anymore. So based on the distant field, they can control exactly like how close or how far away from the feature surface they want to see those eddies, small eddies. So in fact, this is significant because in the past they couldn't see those small eddies. They could, but now this is like for the first time because of this method, they can see those small eddies and how they interact with the feature surface. And so that will really help them to validate their understanding and possibly, right, have some new discovery. Of course, I think it will take probably another few years before they reach the high precision they need, right, to see the fine detail accurate enough. Okay, let me change to another one, another in situ WIVIS solution. And this is a paper we published maybe 3 years ago at WIS. We call it visualization by proxy, also known as explorable images. So the idea is very simple. I already told you that scientists throw away a lot of time steps, right? But what if we can render, like just in situ, a compact intermediate representation of the data, particularly the data they throw away. And most importantly is we render the data, but then we generate, it's not a set of image, it's not a static image, right? Like what most people would do. What we generate is what we call explorable images. So that's why we call it intermediate representation. That is, we don't complete the whole rendering step. We just do it enough. That's why we call it for deferred interaction. That is, we want to allow the scientists to explore this visualization without the original data and without using a supercomputer or a powerful GPU cluster. So this allows scientists can look at their data this way using even an iPad, right, or a laptop. Okay. And if you're interested in the method, you can read the paper. But basically, again, scientists they know a lot about their data, so they can suggest like what I most likely more interesting. So we compose those feature of interest as image layer, and then we output those image layers. So it's like image-based approach, but not exactly. And the storage overhead is not bad. So it's much smaller than a video. So what's interesting about this is you may think, hey, why not just generate a video for them, right? So they can animate over, but then they can browse the video forward, backward. But that's only allow one-dimensional exploration, right? Viewing. But what we want to enable is multi-dimensional exploration. That is, they can explore in, say, transfer function space. They can change color opacity. They can even change lighting parameters. And they can change view slightly, but not a lot. If you allow them to change view a lot, then you need to store a lot of additional data. And also, certainly, they can explore in the temporal domain. So with this, we can recover some discarded data, this fashion, and then this in fact, also a pretty nice previewing solution. Or, as a way to monitor the simulation, but then send back is they can, like over a browser, they can explore the data being generated, and then they can decide if they should change some simulation parameters. So here, just showing that the far left is the store explorable images, and then the second one from the left is what the user could explore, like they change transfer function and opacity, change color and color. This is stay the same, but then they change opacity. And then the third one actually is the ground truth, because what we did is somewhat approximation, but it's good enough approximation. So we just show the ground truth image with the explorable images to show you they are really not that much different. And then another pair example show that we change the we also change the color map. So we run this on the Cray XT5 again. We generate image size 1024 by 1024, and here just want to show you it certainly is more expensive than just you do the volume rendering, because you need to do this additional, we call this IAF compositing. But just here, I just want to show you the number that in this particular case, the simulation, when we use 6400 core, the simulation time take like just over 9 seconds. The I/O time take much longer, but then remember, we don't output every time step. And here, this total time take about 2 seconds, but then again, we don't render every time step. We really don't need, because the change would be so small. It can be negligible. And so, but then if we say we render every 10 time step, then the cost is really just like under 1% of the simulation time. So it's quite acceptable. So let me summarize here. So this is a very viable solution for interactive visualization of large complex data. Particularly, we're talking about data generated by the simulation. So it's also as a way to reduce the data, help you actually maybe reduce data more aggressively, and it's a previewing solution, as I already mentioned. And actually, quite importantly, it may allow you to generate certain visualization you will not be able to generate in a post-processing step. Because during the simulation, you have access to all the data, right? But then unfortunately, scientists have to throw away a lot of data. But during the simulation, you can create a visualization based on all the data you have. And such visualization might not be possible, right? After the simulation is over. So, in fact, we also apply this concept to visualization of vector field. So this is just new result my student generated. Just show, okay, you can look at the vector field using a path line, and then you can recolor it and change transparency, and you can change view. So we have this new result. So it's very encouraging. Okay, so far so good. Now we switch gear. Let's look at the big data problem for information visualization. I think many of you are working on this problem, so I don't need to explain to you where all this big data come from, right? And you guys all contributing to this big data. Actually, every time when you turn on your phone, right, you contribute some data, a few bytes and megabytes, and during my stay, I've been taking a lot of photo and then I upload to Facebook, so I contribute I made my contribution that way. But basically, there's all kinds of data being generated for many different purposes, right? For making good business strategy, right? I mean, the company, they want to know more about their customer, and for fighting crime or fighting terrorism, and for education and for research. So yeah, this list I don't think it's complete, but then I think many of you already working on some of them. Okay, so I'm going to, if I have enough time, I'm gonna go over three projects, mainly three projects, or maybe I should say three topics. So first of all, I would like to look at social network, because right, they're very interested in social network. There's a lot of social network application. So most of the information, right, we can represent the certain relation of interest in the information as a graph or network. And so there are already different way, right? People develop to lay out a graph and then to analyze a graph. So we did some work like as simple as just some mechanism to filter the graph. So in this case, we have a terrorist network. If you lay out directly, that's what you get, because most of the terrorist group, they're tightly associated with one another. And so we develop an ontology-based method, and then also we provide a collection of statistically based methods for the analysts to use, such that they can see structure and pattern from the original data. In this case, we're looking at a particular terrorist group. This is Hamas, like their attack pattern. So all these little green nodes represent attacks. And then there's also label what weapon they use and their target. But the one technique that I want to say a little more is this concept of centrality sensitivity. So I believe you guys all use centrality for studying network.